Right, that seems like a good time to start. Welcome back for the second session, everyone. We're going to start with the third lecture by Masanori Hanada, continuing his Monte Carlo coexistence.
Okay, thank you very much. So I explain actual simulation result. And last time I explained the first part of this section, but I'm sure you enjoy the weekend and forget everything, so I repeat from here. So I have explained how to do Monte Carlo simulation, what kind of regularization we can use, and we actually use those technologies to study game theory. And the most basic example are correspondence between black p-brane and the p+1 dimensional maximalist symmetric theory. And the simulation, we want to solve this theory numerically. And the first thing to do is check the duality by explicitly calculating this side without relying on any symmetry principle. And then hopefully we can go beyond the conjecture, beyond the test by using a numerical method. We want to derive a new result which we don't know, we cannot obtain just working the gravity side. That's our goal. And as I have explained, historically there are difficulties because of fine-tuning problem and the sign problem. But practically, for many important theories, especially maximalist supersymmetric theories we want to study from now, these are not problem anymore. And about sign problem, I will mention a little bit later. And simulation-wise, numerically, p equals 0 is the easiest for obvious reason. So we try precision test at p equals to 0. So it's 0 plus 1 dimensional theory. It's not even quantum field theory, it's just a matrix. And this is in action. This is the Lagrangian. So basically, this is dimension reduction of 4 inner cost to 4 submatrix. So there are 9 matrices, x1 to x9. They are all n by n Hermitian. And we have the superquadrant of x. And this is conjectured to be dual to type 2a black 0 plane. If you don't know what is black 0 plane, you can just imagine it's black hole. And one important difference from 4-dimensional theory is coupling constant has dimension of mass to 3. So we measure energy scale by using this unit. So, and when we take Tofu's limit, this dimensionless combination is fixed. This dimensionless combination scales like L squared. And the strong coupling is lambda, large lambda, but that means if you fix temperature and the lambda becomes large, then this combination becomes small. But if you fix lambda and take temperature T to be small, in the same manner, this combination becomes small. So for many purposes, so for example, when we calculate the energy of the black hole as a function of temperature, low temperature and the strong coupling are the same thing. High temperature and weak coupling are the same thing. And from string theory side, we can calculate the mass of a black hole. And from game theory side, we can measure the energy of the system, and they should be identified. And string theory predicts that this quantity should behave this manner. And some strange poverty appear because lambda has dimension, simple the power counting does not work. And this is a supergravity result, 7.4 times t to the 14/5. And this is weak coupling result in the game theory side. And at weak coupling, energy should scale like this. At high strong coupling, low temperature, if the duality is correct, and energy measured in game theory should go close to this curve.
Is there an easy way to understand the 14/5?
From gravity side, we can understand. And from game theory side, there is no good derivation. But Andres Milgar have some wild speculation. And I don't know if that is correct, but somehow he derived this number. And Toby Wiseman and the collaborators tried to generalize that method to some other theories. And at least, I don't fully understand, but they claim that this strange power, similar strange power appears in other systems like other DP brain or M something brain. And they claim that they can derive the same thing. But that's a very wild idea. It's fun to read. I can tell you the reference later.
Sorry, just a simple question. For the entropy, you have a similar low temperature expansion?
Yes. So basically, D equals to TdS. So slightly different coefficient and T to the 9/5. That's the scaling of entropy. And so calculating entropy and calculating energy are essentially the same. If you accept the thermodynamic relation, So we want to see if how it behaves. And also, I said at strong coupling, if we can measure the energy from game theory side by simulation, results go close to this curve. But of course, there is deviation. Still, there should be some deviation. And if duality is correct at stringy level, difference from this Lie term should behave this manner. And we will check it as well. And I already explained this by using a stupid joke line, but let me repeat. So this theory has a so-called flat direction problem, which means, so you can see this part is kinetic term, this part is potential term, and the potential is commutator square. So if matrices xi and xj commute, then potential is just 0. And that is classical flat direction. And sometimes in quantum theory, classical flat direction is lifted. But in this theory, because of supersymmetry, flat direction survives at quantum level. So if you just naively do simulation, typically eigenvalue becomes very large and the commutator go close to 0, and eigenvalue just rolls to infinity. And the path integral is divergent. And that's feature, and that's not a bug. It's actually physics. And interpretation is that typically eigenvalue of matrices are identified with the position of the D0 branes. And if the branes are sitting close to each other and connected by open strings stretched between them, we have bound state of particles on string. And that is black hole. And in terms of matrix, it's a fully excited matrices. So intuitively, diagonal element correspond to D brane. Off-diagonal element correspond to strings connecting between D branes. And a lot of strings are excited because D branes are sitting close to each other. So strings are short and they are light and they can be excited. So all n squared entries of matrices are excited. This is black hole state. But physically, this particle can just scatter around in infinitely large space. Then strings connecting between D branes are very long and heavy, so they cannot be excited. It's like gas of D branes. But in terms of the matrix, so diagonal elements describe the location of D brane, so they have a non-zero value. But off-diagonal element, which describes open strings, just becomes 0. So this is flat direction. And when particle D branes are sitting far from each other, then force between D branes have a contribution from bosonic sector and the fermionic sector. Due to supersymmetry, they just cancel and they just move freely.
So this is true at 0 temperature?
At finite temperature, you have something like Newtonian potential, but that Newtonian potential is not strong enough to make a bound state if energy is large enough.
So you say that in this model, you will never have gravitational collapse?
Depends on initial condition, I think. Depends on initial condition. So how much momentum each particle has, for example, of how far they're sitting. Of course, if particles are sitting close to each other, if you tune the energy in the right manner, then they should collapse. Anyways, and we can also have 2 black holes, 3 black holes, or all kinds of configurations. So it's good news because we can describe multi-body interaction in this theory. But if we want to do black hole dynamics, of course it gives us some technical challenge. And we have to restrict path integral in order to extract the black hole state we want to study. This is the flat direction problem. And then question is how we can tame the flat direction. And if we go to string theory picture, if we set the string coupling to 0, then this black hole is stable. So black zero brane is a charged black hole and has positive specific heat, and it's really stable black hole. And in game theory side, it should mean bound state of the eigenvalues should be stable. And this can be understood without any detailed calculation. Intuitively, we can very easily understand it. So when we have a bound state of n particles, whose location is described by diagonal element, the off-diagonal elements are also excited, and we have this in a bound state, and all n square entries are excited. And imagine we have such state. We can start with such initial condition. Our simulation, we can start our simulation by choosing such initial condition. And if particle emission or emission of eigenvalue does not happen, our simulation is stable. And imagine such emission of eigenvalue happen. In this picture, it seems this particle is still sitting closer, but actually this particle is very far. Okay, so the slide is not so big. And then strings become very long and heavy, and it just becomes 0. And once particle is emitted, of course, there is almost no force. This particle can move to anywhere. But when this particle tries to escape from others, first this column and row are excited, but they have to simultaneously become 0. And then the particle can be emitted. But we have all the n number of elements here, and they have to become 0 simultaneously. Such process is very rare, and if you wait a long time, it can happen. But typically, there is some entropic suppression. And to see that, we just have to count the degrees of freedom, which is entropy. And typically, such process should have an exponential minus n suppression factor. So when we set n to be very large, such emission should be suppressed, and the simulation should become stable. So we just try to send n larger and larger. And then what happened was, say we took a temperature to be around 1 in the unit of the good coupling. And n equals to 4 is not good enough. So if we take initial condition to be xy equals to 0, x2 equals to 0, and x9 to be 0, then trace x squared divided by n, which describes the typical value of each eigenvalue, the location, distance of radial coordinate of the zero plane. Then it starts with 0 by definition, and it increases, and with something like plateau, what it diverges. So at least one of the eigenvalues is going to rose to infinity. But if we increase value of n to 8, this plateau becomes a bit longer. Of course, we have some fluctuation here, but eventually it diverges. And then we can say if we increase value of n, this plateau becomes longer and longer. Otherwise, black hole is metastable, because eventually it can emit particles and evaporate. But the lifetime becomes longer and longer. Emission rate goes down and down. And if we use n equals to 16, for example, in this parameter, we practically never see particle emission. and simulation is stable, and we can do simulation. And I have already shown this picture, but we can see this pattern and this pattern. And I want to study this as black hole. But of course, eventually we may see flat direction even in such simulation. And this morning I was reading a newspaper, Japanese newspaper, and they say price of the apartment in Tokyo is now coming close to the highest price in 1990. So maybe we will hit the flat direction again, unfortunately. Anyways, so let's see how these two regimes are connected. If we control the flat direction and then do simulation. And there is a long history. Basically, this is a struggle with the flat direction. So in 2007, we did the first simulation. This is weak coupling result. And so in this dotted curve, we took into account a few order of weakly coupled expansion. And at high temperature region, agreement is very well. But as we go low temperature, we start to see some deviation. Of course, weakly coupled expansion breaks. And this is supergravity curve, and we can see that it's coming closer and closer. But here we didn't take Rajan limit, and this lambda is roughly speaking half of number of lattice points. But we didn't send the number of lattice points to infinity. So this was a finite n result without taking continuum limit. So we don't see we have a perfectly good quantitative agreement. But it seems qualitatively it was okay. And we could see that the flat direction can be controlled by sending n to large value. And a few, like 8 months later, Kadyrov and Weizmann did a similar simulation using lattice. And in their plot, they plotted the energy divided by temperature. So at high temperature, it should go to a constant value, which is 6. And they could see that it starts with 6 and gradually coming down and coming close to this black hole result. And here they show two different symbols. And these symbols, which had smaller error, is they could manage to control flat direction. And in some parameters, they couldn't really control flat direction. And they show the result with, but anyway, they show the result with batch configurations as well. And you can see that when they couldn't control the flat direction, error bar is really huge. And it doesn't really make sense. So it clearly tells you that it's very important to control flat direction. Anyways, qualitatively it's already okay, and we are very much encouraged. But it's not good for any fit. And none of us took Rajan, none of us took continuum. And we would say, it could be, maybe it was just consistent with the duality conjecture because of huge error or regularization artifact. Sorry, I forgot to say, but here they encountered the conjecture. And then we did slightly better simulation after 1 year. And we tried to fit the result, taking into account our alpha prime correction. It seems to work perfectly fine. And so we thought we did it, and along this direction, we almost stopped thinking about it. But then, in 2015, Kado and Kamata did simulation using different action and larger n and a better computer. After 7 years, of course, computer become very good. And also, they could use a good computer because I wrote application to the supercomputing project. I took time, and they used it to kill my result. Anyways, so they did the simulation to challenge me using the supercomputer results which I took. But results look very similar. But this is our fit. This is their fit. Taking into account this term, and the fit result look very different. And if we plot these two things on top of each other, so these white symbols are ours, green and red are theirs, and there's small deviation, but this deviation is already crucial. We cannot really precisely determine string correction if we have this amount of difference. And of course, this difference does not mean either of us did anything wrong. So both of us did finite n, finite cutoff simulation. None of us took large n continuum. So we thought that we have to take large n and continuum. And of course, the strategy is burn more electricity. And we did it. So we used lattice regularization, and we used parallelized code, which is for matrix model. I never saw any parallel code, so I just invented everything by myself. But I'm not a really good programmer, so it's not really optimal. But I explain what I did. Okay, so first we have only one time direction. So we divide the time direction to be several sub-lattices. So, we introduce lattice on this time direction, and we have, say, 30 or 40 or 50 points. And we just introduce sub-lattices consisting of 5 points or 4 points. And each CPU can take care of small lattice and they can sub-lattice and they can work together. But typically in lattice QCD in 4 dimensions, for example, we have 4 dimensions, so each direction can be split to lattice, and if you have 10 lattice along each direction, then you can use 10 to the 4th CPUs. But in our case, we have just one direction, but rather we have huge metrics. So if we just divide the temporal direction to sub-lattices, actually we cannot really use the power of parallel computer. What we have to do is we have to divide matrix to sub-matrices. But anyway, you can imagine that we have a kind of local space, and that matrix multiplication is something like you can imagine matrix is something like non-local lattice. Anyway, so we see matrix direction as if it's kind of lattice, and we divide matrix to sub-matrices and write the simulation code for that, and burn a lot of electricity. So typically, we cut the temporal direction to be, say, 10 sub-lattices, and we divide matrix to be 10 by 10 sub-matrices, in total 100 sub-matrices. Then we can use 1,000 CPU to study this system. And it runs very well.
But sorry, I missed something. So, as you said, the matrices multiplication, so the way they interact is completely non-local. So how can you, precisely and efficiently decompose in blocks on the time direction? That's the usual thing.
So we're not local or non-local. So that means so here in this direction, interaction is local.
Yeah.
So typically we need some communication between neighboring lattice nodes, sub-lattices. Mm-hmm. But this block does not have to communicate with this block. It has to communicate with this and this only.
Okay. Yes.
And if you take matrix multiplication, so multiplication is like this row and this column has to be multiplied. Yeah. So this block has to communicate with all other blocks on the same row and all other blocks in the same column.
Yeah, and it's even worse because you have degree 4 interaction. So you have you multiply the matrices.
Basically, every time we have multiplication, we need communication.
Yes.
So in that sense, whether it's a 4-point, or 5-point, or 6-point interaction, that doesn't matter much.
Okay.
But definitely, communication is a lot more expensive. And I think there should be better way to solve this problem. But what I did was I just introduced a lot of communications, which is may not be a good idea in this large-scale computation. But I try to avoid as much communication as possible. And then after doing our best for writing code, we use a lot of electricity. And for that, of course, we have to use a big supercomputer. So I talked to people in Livermore Lab in California, and we started Monte Carlo string M theory collaboration. And of course, we chose this name because MCMC is Markov chain Monte Carlo, and the MCSMC sounds like MCMC. You know, this Evan Berkovits cooked up that name. And Evan Berkovits and Enrico Rinaldi were postdoc at the Livermore Lab at that time. And now Enrico is in Brookhaven and Evan is in Jülich, in Germany. And they are lattice QCD postdoc, but also interested in this kind of business. So if you want to do such simulation, they are the right people to talk. And we took a simulation time from K supercomputer in Japan and Volcan in Livermore Lab. And I don't know what the meaning of Volcan, but this is the only thing I could come up with. And I think this is the name. Volcan should mean these people, but I don't know why this computer should be called Volcan. But that's how they named it, no way. And we used, so for lattice regularization, I said in the case of 0+1 dimensional theory, thanks mainly because of UV finiteness, we don't really have to take a complicated SUSY preserving action. What we did is very simple. So we actually fixed the gauge degree of freedom, which is technically gives some technical advantage. And so we first introduced a gauge fixed action with gauge fixing term, and then just regularize that gauge fixed theory by using naive lattice method. So, basically, you take a difference between scalar at point t and the point t plus a. This a is lattice spacing, so it just means nearest lattice points, and take the difference, and that is approximately derivative, and you just take square, that's the derivative square. And here we have unitary link variables in order to make derivative to covariant derivative. That's it. And for fermion, also we used rather naive regularization. And this is so-called naive action, which has a bigger regularization artifact. But we can order some more terms to make lattice artifact smaller. The basic idea is that tune the action so that when we compare 3D level action and when we compare lattice action and continuum action, we expand lattice action in power of lattice spacing A, but we tune coefficient of lattice action so that order A term disappear and the correction starts from order A square or something like that. And we can easily do that. And we tried both, and we confirmed that they give the same continuum limit. But sanity check. And this theory has fermion sign problem in the sense we integrate out this fermion phi, which is in this action, and then we get the. So let's just write this SF to be. So this is bilinear with respect to psi. So let's write it to be psi d psi. Okay. And we have after integrating out the fermions, we have a Paphian of D. Here we get Paphian because fermion is real. Fermion in this system comes from 10-dimensional Majorana Y fermion, and that gives some reality condition to fermion. So instead of determinant, we get Paphian, which is something like the square root of determinant. And the determinant is not real positive, and the Paphian is not real positive in general. And this is the sign problem. So because this particular way, is not necessarily real positive, we cannot directly use Markov chain Monte Carlo. And we use the so-called phase quench approximation, which means instead of perfume, we just use absolute value of perfume and throw away phase factor. And in general, such approach doesn't work. And for example, in finite density QCD, if we do the same thing, we get the wrong result. But as I will explain later, in this case, we can justify this approximation numerically, and we get the right answer. And for this kind of simulation, in order to give some idea about how much money we are spending, this is a screenshot of my laptop in one day in probably March last year. And this, so I connected to Vulkan and I submitted a lot of jobs. And when one job is done, then it's resubmitted automatically. And of course, here actually more jobs continue, more lines continue. But typically, so this is a number of nodes, 32, 16, 2, and each node contains 16 CPUs. So 2 means 32 cores, 32 means 512 cores. And typically, for this project, I used 2 to the 64 nodes. Actually, it's slightly different project, but more or less the same. And so it means 32 cores to 1,000 something. But 100 jobs are running regularly. So it's not cheap, but it's cheaper than big simulation in lattice QCD or Astro calculation. Anyway, this is more of the scale of the simulation. Okay, so for example, what we do? So we study, for example, we measure the energy divided by n squared. This is a good quantity which scales like order n, order 1. And we calculate it at each, so for each fixed n and each fixed temperature, we measure the energy for different lattice size. And we take continuum limit. Okay, so here we call number of lattice size to be L. So we did simulation for 8 lattice size, 12 lattice size, all the way up to, so probably this is 64 lattice size. And then we fit the result by polynomial. So constant plus 1 over L plus 1 over L squared. And we can see that two different regularization with the same continuum limit. And of course, we have to check that different data give different extrapolation result and so on. We did all kinds of statistical analysis. And also, in order to take large n, we have to study different values of n as well. So typically, we studied n equals to 16, 24, and 32 for various different lattice sizes, and assumed this extrapolation results. So leading part is large n continuum piece, and we assumed correction. So 1 over L at large n, 1 over L squared at large n, and the constant part of 1 over n squared. And of course, in general, we have to introduce terms like 1 over n squared L, or 1 over n to the 4th, or 1 over n to the 4th times L, and so on. But of course, because we have already limited number of points, we cannot introduce too many fitting parameters. And this is the fitting parameter we used. But then from this coefficient, we can estimate large n continuum result, and also 1 over n correction in continuum. Okay, so this was the result we wanted to test. Okay, and we got large n continuum result. Large n continuum should be this piece. This part is 1 over n correction. Okay, and let's see if we can reproduce this result. For example, if we assume these powers and introduce three fitting parameters, what we get. And this is the result. So this was a previous fit result by us and by Hanada. And these are our new simulation data, simulation result. And this is our best fit with these standards. And it says coefficient of t to the 14 over 5 is 7.4 plus minus 0.5. And theoretical value was 7.41. And these two coefficients are now minus 9.7 plus minus 2.2, and 5.6 plus minus 1.8. And previously, we didn't take into account this term, and basically it also only considered this term, and say the coefficient was minus 5.55. But it seems that this we got this value because we didn't take into account this part. And t to the 4.6 and t to the 5.8, its power is not very far. And so they look rather similar, behave rather similarly. And if you just add up minus 9.71 to 5.6, the result is actually close. So the coefficient looks very different actually. Actual values are not much different. And of course we tried various other fitting methods and observed that the result, fit result is stable. And okay, so now I said with this fitting methods, A is 7 point plus minus 0.5. But what we wanted, if the derivative were right, were 7.41.
So can I ask about error bars exactly? So what do you take into account there? So there are the well, you're doing Monte Carlo, so lattice sizes, finite size effects.
So
there are the quench phase.
So we did phase quench, and in this plot we didn't estimate the error of that approximation.
Okay. And
what we did was at each t, we did large M continuum extrapolation by using this and that.
Mm-hmm.
Then at each fixed temperature, we can give error bar.
Okay.
And taking account of this error bar, we did the numerical fit.
Okay.
And then we get this error bar.
Okay. And what about the integral over the unitary group that you have to perform, because you have to so the gauge fixing. So
So we introduce Fadek pop-up term corresponding to that. So,
okay.
So even if we use the usual gauge no-fixed action, we should get the same result. That we can theoretically show. There is no approach.
So at the end of the day, it amounts. You have to do this integral over unitary over U.
But so we treated gauge fixed action in a correct manner. So result is the same.
Okay.
After taking continuum.
So you have the ghost in your fields and.
Yes, yes. And in our simulation, that effect is taken into account. Okay, so we could reproduce this term. At least when we use this fitting methods. And then what about this correction, this term? So we expect 23 over 5. Because if we, for example, ideally, if we can just leave this term, this term, this term, if we can introduce, if we can make all terms as free fitting parameter, of course that's ideal, but we just have finitely many points. So we cannot introduce too many fitting parameters. So let us cheat a little bit. So here, we wanted to do 4 parameter fit, but that's too hard, because we don't have many points. So we assume that this power is not determined, but the difference of the power is 6 over 5, which we expect from alpha prime version. Okay, so in that sense, it's not really 100% perfect treatment. But then we have only 1, 2, 3 fitting parameters. And we did it. And this is our result. Very good. And also now.
Sorry, so you didn't show us the fit for 14 over 5, or I missed it.
Yes, that's I.
Why do you want
so here I'm still cheating because we didn't leave it free, right? But for example, if we leave this to be undetermined and this to be this undetermined free parameter plus 9/5. And so this power to be this power plus 3. Then actually we can get 14/5. And we did all kind of it. But in a published paper we didn't show that. But maybe in the next paper we should explain that I'm thinking. But anyways, and also now we are increasing more simulation points. So this is preliminary result. And we added these points, new points. And here we use different color because we haven't taken large and limit yet. And by adding more points, we want to make fit more convincing by reducing number of answers. And what I can say is, so this work is still going on, but now we obtained 14/5. And you can see that if we go read this low temperature, then alpha prime correction becomes very small. And the 7.4 and the 14/5 should be obtained. Anyway, then what about 1/n correction, which is another interesting part? Yeah, for example, if you see finite coupling correction at large n, so here we are not using symmetry, but people would say, yeah, but still, if we look at, for example, integrable sector before the n equals to 4. Of course, they have to rely on integrability, but they can see nice agreement between finite coupling correction and alpha prime correction. But I think 1/n correction is something even harder. And I want to claim that numerical approach can work even for that. So GS correction in gravity side is calculated by Hyakutake, and his calculation is very hard, so I cannot really follow. But so this first line was our numerical result, and he calculated the 1/n correction from gravity side, and he said those numbers written in red letters can be determined explicitly. And these blue ones, A, B, C, cannot be determined without knowing further detail about higher derivative correction. And we want to see if we can reproduce this expansion from game theory simulation. And first, this is the result. This is a result we obtained by using n equals to 345. For some technical reason, we could study very low temperature region. And this is the result we obtained in 2016 from n equals to 16, 24, 32. Here error is very big, here error is rather small. And this black curve, minus 5.77 times t to the 0.4, it's this term. And also by introducing one free parameter, similarly we can fit the result. So in this low temperature region, this term doesn't really matter. And at low temperature region, a high temperature region, error is big, so you shouldn't take it too seriously. Anyway, and I claim that this explains, this 1/n squared term can be correctly reproduced from game theory. And how can we see that? How can we obtain this plot? So firstly, here, we did simulation for various lattice size and various values of n at each temperature, and we did this extrapolation to continuum the large n. But as a byproduct, we can get coefficient for 1/n squared term. And this is the result. And the error bar is very big because n is big, 1/n correction is very small. So fit is not easy. When 1/n correction is big, of course, we can easily see how the dependence on the 1/n squared. Okay, and here, if you want to know the technical detail, I can explain more. But basically, for technical reason, at a very low temperature, problem with flat direction become milder at a very low temperature. So n equals to 345 could work, and then we can fit coefficient of 1/n squared term rather easily. And if you zoom up here, this is our simulation result. So these are the coefficient of 1 pi squared obtained from n equals 3, 4, 5. And here, we don't have error bar because we just had n equals to 4 and 5 at this temperature. And this dotted line is minus 5.77 times t to 0.4. And the agreement is very good. And also, if you see this expansion, at the very low temperature region, higher order term with respect to T should be negligible. So agreement at leading term is means that we are on the right track. And I didn't explain why sign problem can be ignored. So I have to explain some detail, I think, because I have 15 minutes. Okay, so what was sign problem? Just let me repeat again. So in general, we can imagine we could write action to be bosonic part plus fermionic part, and the fermionic part is written in this form, fermion bilinear. This is a Dirac operator, which in general depend on bosonic field. And then we can integrate fermion by hand, and we can get this effective action. In the case of supermelt, this determinant can be Papian, but essentially they are all the same. And unless this integral weight is real and positive, we cannot use Markov-chain Monte Carlo directly. And this fermion determinant sometimes become complex or negative. This was a sign problem. And as I explained before, oh, I just don't have to repeat the same thing, I think. But yeah, so this is a slide I used before. So why that was a problem? Because we want to use we want this integral weight to be probability, okay? But this expression is actually crucial. This is a definition of the expectation value. But in maximally supersymmetrical mills, determinant of Papian is complex. But of course, if we use this combination, this is positive, and we can do simulation. But the problem is, this is not necessary. The phase factor, in general, change result. Okay, and the crucial thing was we can rewrite this exact definition. This equality is just by definition. But we can rewrite this determinant with phase times absolute value. And we can multiply. So this and this are the same. And this part is just the same, this. And we have, we multiplied 1 to that expression. So this part and this part are exact same. So we divide both numerator and denominator by the same factor. It does not change anything. But then numerator and denominator looks like expectation value of phase, and phase times of observably phase point action. Okay, and the problem was this looks like 0 divided by 0, where phase fluctuates a lot. However, if you look at this expression, you notice this. If in Monte Carlo simulation, in general, we have some distribution peaked around some important configuration. So we do important sampling, and if we plot the value, if we make a histogram of observable, like energy or product flow or whatever, typically we have some peak around average value because we are doing important sampling. Okay, and imagine this phase factor calculated for fixed value of observable. So imagine, so you fix the value of energy, and you measure the phase factor for each fixed value of energy, and you make you plot it as a function of energy. And imagine the phase factor is constant when this distribution has a non-zero value. If this is just constant, it means phase. We can write this phase quenched expectation value as the integral of x times distribution function rho. Okay, and imagine when rho is non-zero, phase is constant. What does it mean? And this numerator is written as integral of x times rho of x times phase at each value of x. And this is written as rho of x times value of phase at x. So here we don't have x here. But this phase is constant anyways. And let's call that constant to be c. This is just c. And here, because this is constant, whenever this is non-zero, you can just regard it as overall constant factor c. And they just cancel. And the phase quenched value and the exact value are the same. And of course, you would not imagine why such a miracle should happen. We don't expect it. However, if we actually make this kind of plot, this is actually the case for supersymmetrical meals. We don't know why that happens, but we just plotted phase at each fixed value of energy or fixed value of scalar eigenvalue, and we observe this pattern. And we can see that away from the peak, actually there is some observable dependence. But such configuration do not contribute to path integral. And in 0 plus 1 and 1 plus 1 dimension, we numerically checked it. And of course, here we could do such test, such justification, only when we can calculate this quantity, phase for fixed value of observable. And if it becomes too close to 0, we cannot do such calculation, and we cannot really check this is the case.
If what goes to 0, t?
No, this phase. If phase fluctuates too much, if this average becomes too close to 0, then error becomes very big. What happens is it goes very close to 0, and essentially you can imagine, you can see something like plateau, but error bar is too huge. And even if function it has some non-trivial form, if error bar is too big, it looks like a plateau. Okay, and if that happens, why do you believe that result? However, empirically, we know that Polyakov loop and phase are very strongly correlated. And we try to see if Polyakov loop and other quantities are correlated or not. And here, we plotted I forgot the value of n, but n is very large. N is 16 or something. And we try to see correlation between Polyakov loop and energy. Okay, so we made a two-dimensional distribution. So we have a lot of configuration. So we measure Polyakov loop and energy from each configuration, and we made a two-dimensional plot. And for example, if we fix energy to be in this beam, or this beam, or this beam, we can make a distribution of the Polyakov loop for fixed value of energy. And regardless of the value of energy, we see exact same distribution. And by fixing the value of a Polyakov loop, which probably correspond to fixing the value of the phase, okay, and we can make a distribution of energy. Okay, so we just select the configuration in this band, this band, this band, fixed value of Polyakov loop, and we make a plot of the energy, and distribution is exact same. So Polyakov loop and energy are not correlated at all. We don't know the reason, but this is a numerical observation. And we accept the assumption that phase and the Polyakov loop are strongly correlated. It means energy and phase are not correlated at all. which is equivalent to this statement. So some miracle is going on. We don't know why, but numerically we can observe it. So we believe phase range approximation is correct. But if we can understand it analytically, of course, this is very good, much better. And I want to spend 5 minutes for new result, which will appear soon. And we want to use numerical simulation to test new duality proposal. And we studied 0+ 1-dimensional gauge theory. What if we do not impose gauge symmetry? There are many motivations to do that, but I have just 5 minutes, so just let me explain the result. If we integrate out AT by hand, it is equivalent to imposing a Gauss law constraint. So if you take AT equals to 0 gauge, then from gauge fixing condition, you get this. So, sorry. First of all, equation of motion of AT is written like, because kinetic term is like this. If you write down the equation of motion of AT and set AT equals to 0 as a gauge fixed condition, then you get this Gauss law constraint. In operator language, this combination is a generator of gauge transformation. So this Gauss law constraint, in terms of Hilbert space, means the physical state has to be gauge singlet. And removing gauge field by hand, just consider ungauged theory, means remove gauge singlet constraint, and the gauge non-singlet are allowed to exist. And let's ask what happens if we consider such theory without gauge singlet constraint. And in string theory language, gauge singlet is closed string, and the gauge singlet, non-singlet is open string. For example, if you have a state, okay, trace or product of X acting on vacuum, intuitively you can imagine that you have 4X, and imagine if this term, in this trace we have xik, xkl, xlj, xji, and so here because we take trace, we should take sum with respect to I, j, k, l. If in gauge non-singlet, we don't have this cyclic pattern of indices. Okay, and this time intuitively you can imagine that. So starting with ith different, this ik component element describes open string connecting ith and kth different. So you have this open string, this open string, this open string, and this open string, and it always comes back to the same point. So Hilbert space is this physical state, gauge singlet state, is described as open string made of a bunch of closed string made of a bunch of open strings. And if you don't have gauge singlet constraint, you don't have to consider closed string only. You can also take with account open string. And so if we consider gauged matrix model, black hole state is black hole made of closed string only. So you imagine long winding closed string, which is black hole. And if we remove gauge singlet constraint, so we should consider black hole made of open strings. And there is no natural place where in the bulk where open string can end. So what Fuan recently suggested is that, okay, imagine open string is attached to some boundary. Then open string comes from boundary, and in the bulk, it makes something like black hole, and open string goes back to boundary. Suppose this is a dual gravity picture, but a dual string theory picture. This sounds natural, but then intuitively, what can happen? String can self-interact. So here, this string can interact with itself, and then it can pinch off to shorter, and then we have a long cross string in the bulk and a short open string at boundary. And of course, if string becomes shorter, energy goes down. So string wants to become shorter. So this open string attached to the boundary just become shrink and shrink and shrink and almost disappear. And this piece just go towards the black hole itself. And so this it just should just look like the usual closed string. So duality gravity dual should be usual black hole described by gauge matrix model plus some short open string hovering near the boundary. And to some extent, in gravity side, it's possible to estimate the contribution from such short open string. And if we calculate partition function, correction is something like n squared times some integer. It can be 1 or 2 or 3. And exponential of some unknown constant times 1 over temperature. Quite generally, we can make such estimate. So if this picture is correct, that means gauged matrix model and ungauged matrix model should be very close. And the partition function is when beta is 1 over temperature. So when beta is infinity, or beta infinity means 0 temperature, then partition function, you just have this exponentially suppressed correction. And if you calculate energy from this partition function, for example, energy in gauged matrix model and energy in ungauged matrix model, difference is just constant times some unknown factor times exponential minus 1 over t. And the string theory picture, just the short open strings are attached to the boundary. So even without gauge symmetry, it's possible to have a perfectly good gravity dual, and the gauge symmetry does not have to be crucial. But of course, unless we have gauge theory, but I don't know, we have some concrete numerical value in field theory side, we cannot really make sure that this picture is justified. So we did simulation. So we already did simulation for gauge theory. So we repeated the similar simulation for ungauged theory and took the difference of the energy.
No, this was already done for the one matrix problem.
Yeah.
In one matrix probably, yes. And that's of course, that's the reason why F1 got interested in this case as well.
But in the one matrix model, then it's completely different, right? Between gauged and ungauged.
No, they have the same formula. Because in the previous transparency, I included a formula.
But I thought in the one matrix
This kind
model,
of
the
picture.
gauged.
This one right here,
This kind
that's
of
the
picture.
giant state, and then it multiplies.
Yeah, but
the
then,
gauge.
so the gauged one matrix model is equivalent to n free fermions.
That's right.
So the energy and the entropy and the free energy are of order n. Whereas the ungauged one matrix model is supposed to be like a black hole with an energy of order n squared. So it's an entirely different large n limit. Right? So I think what you're saying is true for if you have at least two matrices.
Is it related to black hole non-formation story?
Yes.
Because of
Yes,
matrix
it's
model.
related to
Yeah.
that.
And here we are talking about the black
Yeah.
hole state.
So when you have more than one matrix, then things are different. But then the fact that the gauged and ungauged match at high temperature, I think is well known for many, many years.
High temperature region, at the high temperature region,
They match.
if we go to very high temperature region, so in a sequence, you mean 2
No, in
minutes?
any model. So you take any matrix quantum mechanics. That's a completely general result that you can
High
do.
temperature, actually at high temperature there's a quantitative difference.
They match.
No, they don't match. For example, in BFSS matrix model, when energy are different. Like
Gauged and ungauged?
Yes.
No.
Because if you go to high temperature, in order to count estimate free energy, basically you just have to count the number of degrees of freedom.
Mm-hmm.
But without the gauge symmetry, you have more degrees of freedom. And for example, you can calculate, so then I say the high temperature behavior is, at high temperature energy is like 6 times n squared times t. We can easily calculate that.
Mm-hmm.
And in engaged model, we can also analytically calculate it. And value is 1/8 bigger. Because of gauge symmetry, so essentially we have only 8 matrices in gauge theory. Without gauge symmetry, we have 9 matrices. And that gives 12.5%.
But that's not the gauging of UN, if you remove. Okay.
So if we remove gauge symmetry, we have one more physical matrix.
Well, we're going to talk about it.
Yeah. But it's true that people thought at high temperature, gauge symmetry is at least a qualitative level, not important. People typically say, yeah, because it's deconfining phase anyways, we are saying color degrees of freedom manifestly. And that is true at qualitative level. But here, very counterintuitive thing is we have to go to lower temperature to see the agreement. So we are not taking a high temperature limit. And in this case, for example, here I wrote that difference is, so beta is 1 over temperature. This difference is 1 exponential minus 1 over temperature. And close to 0 temperature, difference disappears. But if we go to high temperature, difference becomes bigger and bigger.
I'm very confused now because there are models where you also have this Hagedorn phase or this Hawking-Page phase transition. This is possible only in the gauged model.
Yes.
It doesn't occur in the ungauged model, which means that the low temperature phase of the gauged model is entirely different from the low temperature phase of the gauge model.
I will show you the Bosonic version of this theory as well, in which
because there, at recoupling you can compute, right? These are old papers where it's well known that that you have it's a completely different behavior at low temperature.
I think we have confusion about the data statements, small confusion. And it seems that so our paper will appear soon, Juan's paper will appear soon, and his new paper he tried to explain that apparent contradiction, and he tried to solve it. Anyways, so here we tried two different expression hazards. When we use the smallest include the smallest lattice for extrapolation or no. Anyway, so you can just imagine we did 2 different hazards for continuum extrapolation. Result doesn't change much. And the point here is this C is undetermined. So there is no prediction for that. But this D has to be integer. It counts the number of states of adjoint. And so here we have 3. This is a log plot, and we have 3 curves. 1 times exponential minus 1 over t, and 2 times exponential minus 1 over t, and 3 times exponential minus 1 over t. It turned out if we numerically fit it, actually, D should be 2, and C should be almost 1. It doesn't have to be integer, but somehow it's close to 1. And if C is 1, then it is just D times exponential minus 1 over t. Lambda is set to, you can imagine lambda is just 1, as usual. Okay, and somehow, you can really see that agreement is very good. And here we already looked at energy, but for example, if we see such quantity, I need over or minus sign. For this, for the same argument, we know that we see the same exponential decay with the same factor C. But here, overall coefficient can be arbitrary. There is no theoretical control. And sorry, here, it's preliminary version. We have 3 different extrapolations, but actually this green one is the most trustable one. And we can see that decay pattern can be described by using same exponential. So here, this dotted line is 3 times exponential minus 1 over t. But the slope is exact same. So it decays in the same manner. And this is the result for supersymmetric theory. But we can do the same numerical exercise, Bosonic version of matrix model, which actually has confining and deconfining phase. And in ungauged theory, of course, we have only the confining phase. In the sense, product group is always non-zero.
In the
It's always one. Ungauged theory.
in the N-gauge, you have only the non-confining phase.
Non-confining phase, yeah, you're right. And in confining phase at large n, for example, energy or trace x squared becomes constant. We know that it's so-called Eguchi-Kawai volume independence. And this is a result obtained from ungauged theory simulation in a temperature region which corresponds to confining phase of gauge theory. And we can see energy goes to constant value. And actually this is a constant value is the same as constant value in confining gauge theory. And at zero temperature, it just goes close to that constant. And the deviation is something like exponential minus 1/t. And for other observable, we can see the exact same exponential decay. And in this case, both shows like a difference from constant value is exponential minus 2.1/t. And the exponent is just the same. And in this case, probably we should understand it as regardless of gauge singlet constraint, ground state is gauge singlet anyways. So it's not surprising that at zero temperature we get the same value. And the difference corresponds to mass gap. So gauge adjoint state has some mass gap, and that mass is described as exponential decay. And this is my final slide for this section. So gauge symmetry may not be essential for the duality, at least in this case. And we don't know if this result generalizes to other dimension. And I don't know if similar statement holds for generic quantum field theory. And if that's true, then it may solve various technical problems associated with lattice regularization, or sign problem, or Hamiltonian formulation. Because there are several technical problems which can be gone when gauge singlet constraint is omitted. And for gauge theory, we also calculated Wilson loop, correlation function, and also we also studied the theory with less supersymmetry, and we tried to see how eigenvalues interact. And we can do really many things in this direction. But these work are really old, and we didn't even take continuum limit, so it's better to rerun simulation and get much better with more precise result. And also that way we can do something beyond the test of the duality, I think, because computers are getting more and more powerful. It's time to do that, and many more things to do. So by using GPU parallelization, maybe we can do simulation more cheaply, and we can do many interesting things. Or maybe we can use a more efficient algorithm, which are invented by lattice QCD people. And 11-dimensional supergravity should be described by BFSS matrix model. And according to Masanori, Shiki, Jabari, and Fan Ramsdong, M2 brane or M5 brane should be described by VMN matrix model. And also, it should be possible to see more non-trivial dynamics by studying more interesting quantity. And all of these things are about matrix model. But the 4-dimensional super-MLs can, in principle, be studied on computer. What we have to do is we just have to write good simulation code and invent good algorithm. We know regularization itself already. And even more interesting is real-time simulation. And anyways, it has just begun. There are many interesting directions to be explored. Thank you very much.
Is there any quick question that someone would like to ask? If not, let's thank Masanori again. We can take